Good morning, one and all.
Good
Good
morning,
morning.
So,
ma'am.
with respect,
Good
yeah.
morning, ma'am.
So, I gave you three homework problems, assignment questions. Did you solve?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay. Okay, fine. Others,
Yes,
Yes,
ma'am.
ma'am.
please do not leave it as it is. Okay, whatever assignment questions I give, please solve. Next, coming to today's topic of discussion, that
Ma'am,
is
could you just
capacitive.
maybe mention the results or something?
Okay, you want answers, is it? Um, okay, for eighth question, what did you get? Yes, guys, can anyone tell me?
First
Ma'am,
one,
for eight.
Ma'am,
0.3375 volt.
ma'am, I got
Yes,
first
ma'am.
one 0.4. Is that fine?
0.4, is
Ma'am,
it?
the first part will be 0.334.
Correct. Correct. 0.34 you will get. I'll
And
write the
And
zero
answers here.
point 0.1625.
and the next one will be
0.1625,
0.16
ma'am.
volts.
Second part.
0.1625
Volts.
25.
25.
25.
is it?
Yes, ma'am.
They're asking you to find minimum and maximum forward voltage drop. Okay. This is voltage values. And next coming to the dynamic resistance, what did you get?
1.226 ohm.
1.22.
226.
1.23 ohms and
1.23 ohms.
1.54 ohms, is it?
52. Ma'am,
Yes,
52.
ma'am.
Yes,
Okay,
ma'am.
that is fine. That is fine.
1.6 I got. Is that fine?
Okay, that's okay, no problem. Okay, next coming to ninth question. Ninth question, you have A, B, C. Can anyone tell me what answers did you get?
Ma'am, for
A
Ma'am,
A, it
A
is
is
1.125.
1.667
1
125.
point,
amperes.
1.67
1.67
amperes.
and
Yeah. And
1.25.
IT2
1.25 amperes.
1.25. Yeah.
Yes, ma'am.
Correct. And then voltage
B is
value, it is 0.81
0.77.
volts. Point 0.8, okay, 0.
775.
775.
Okay. Next coming to dynamic resistance, 1.3 ohms and 1.52 ohms.
Yes, ma'am.
Yes,
I
ma'am.
Yes,
Correct?
got
ma'am. Yes.
1.51.
Yeah,
Ma'am,
That is
1.51.
1.51.
that's okay. That's okay. No problem. Next, coming to fourth question, 10th question. Can anyone tell me?
Ma'am,
Ma'am,
1 ohm and
1
0.
ampere,
Yeah, 1
1
ampere and
ampere.
0.714
1
amperes.
ampere.
Maximum.
Yeah.
Yes, ma'am.
Yes, this is the answer. Okay, fine. Next, coming to today's topic of discussion, that is capacitive effects of a PN junction diode. So with respect to this capacitive effects of a PN junction diode, we have two major effects. One is transition capacitance, transition capacitance, or the other name is depletion layer capacitance. So one of the author, he will use transition capacitance. If you refer some other book, and he will be using, the other author will be using depletion layer capacitance. So please do not get confused. Make a note of both the names. And the second type of capacitive effect is that diffusion capacitance. Diffusion capacitance. Okay, the major difference between these two capacitive effects is that the transition capacitance occurs at the junction of a reverse bias diode. I'll mention it here. This occurs, okay, at the junction of, this occurs at the junction of a reverse biased diode, wherein the diffusion capacitance occurs at the junction of forward bias diode. So we shall see how what is the principle behind these two capacitive effects. First and foremost, coming to transition capacitance, represented as C with suffix T. So when a diode is reverse biased, so the basic idea with respect to this transition capacitance is that if I consider, Anirudh, can you mute yourself?
Sorry, ma'am.
Anirudh?
Yes, ma'am.
Okay. So if you consider a PN junction diode, okay, here you know this has got majority holes and this has got majority electrons. This is P side and this is N side. And here how the junction is formed, all those things, you know, this is filled with negative immobile ion and this is filled by positive immobile ion. Okay, this is a simple PN junction. Now, so what happens when you reverse bias a PN junction diode? It means that what happens when I connect this to negative of the battery and when I connect N side to positive of the battery? You know, as you increase the potential, the depletion region, it widens, correct? So here whatever you are seeing, I can mention this as a depletion region, or the other, I can also call this as a dielectric. And these two, the junction, these two behaves like the plates of the parallel plate capacitor. Okay, I can call this as a dielectric. So as you increase the reverse bias voltage, the dielectric or the depletion region, it widens. Okay, so when a diode is reverse bias, the depletion region around the junction, it behaves like a dielectric. So as this region is free of carriers, this does not contain any of the carriers. This contains only the immobile ions. Okay, so the width of the depletion, as the width of the depletion region increases with increase in the reverse bias voltage, the distance between the two parallel plate capacitor increases, it widens, correct? So therefore the dielectric between the two conducting plates acts as a capacitor. So it can be given by the equation Ct equals epsilon A divided by D. You know, epsilon represents the permittivity of the dielectric between the plates, and D represents the distance between the parallel plate capacitor, and A represents the area between the plates, and Ct represents the transition capacitance. Let me mention over here, Ct represents transition capacitance, epsilon represents the permittivity, A represents the area between the two parallel plate capacitor, and D represents the distance between the two parallel plates, or the distance between the plates. Did you understand how the transition capacitance has come into picture? You want me to repeat again?
Yes, ma'am.
Yes, ma'am.
Okay. If you consider a diode, okay, and if you reverse bias this diode, it means that P you are connecting it to negative of the battery, N you are connecting it to positive of the battery. So if I write in terms of the internal P, in terms of the basic block of PN junction, you know how the junction is created and how the immobile ions are formed, correct? So what I do is that P side I'll connect it to negative of the battery and N side I'll connect it to positive of the battery. Transition capacitance, basically it occurs at the junction of a reverse bias diode. Okay, so when you reverse bias the PN junction diode, as you increase the reverse bias voltage, okay, the depletion region widens. Correct? And how this junction is formed and all those So since this depletion region increases, and inside the depletion region you have what you have inside the depletion region. This contains basically an immobile ion, right? Those are not carriers, those are not charge carriers. Those are basically immobile ions. The large number of immobile ions you can find with respect inside the depletion region. I can call this as dielectric. Okay, this forms a dielectric, and these two forms the parallel plate capacitor. This forms a capacitor. This behaves like a parallel plate capacitor. Okay, so therefore I can write with respect to the equation, you can give this in terms of equation, that is epsilon A divided by D, epsilon A, D, all those things you know. Okay, so therefore when a diode is reverse biased, the depletion region, whatever you have, around the junction, it behaves like a dielectric, as this is free of charge carriers. So therefore the width of the depletion region increases with the increase in the reverse bias voltage. Did you get? Did
Yes,
you understand how the transition capacitance is formed? Next, coming to diffusion capacitance. The next capacitive effect, diffusion capacitance, represented by CD. So I mentioned initially diffusion capacitance, it occurs at the junction of forward bias diode. So when the diode is forward biased, it means that P you are connecting it to positive of the battery, N you are connecting it to negative of the battery. So what happens when the diode is forward biased? What happens to the depletion region?
It becomes thinner.
It becomes thinner. As the depletion region, the width of the depletion region decreases, more and more number of charge carriers flows throughout the circuit. Correct? So under diffusion capacitance, what happens is, with respect to diffusion capacitance, I can give you the equation CD is equal to dQ divided by dV. So how do you explain this? So diffusion capacitance is basically, it is called as incremental capacitance given by the rate of change of injected charge carriers with respect to voltage. Okay. As the charge carrier increases, the diffusion capacitance increases. In the sense, the majority carriers which are flowing through the circuit, that is the diode current, increases. Did you understand? So
could you explain again
okay.
this rate of change?
Okay. So under diffusion capacitance, this occurs at the junction of forward bias diode. This is one fundamental. This is one what I can call this. You have to note. Whereas transition capacitance occurs at reverse bias, whereas diffusion capacitance occurs with respect to forward bias. Okay. So what happens when diode is reverse biased? What happens when diode is forward biased? These two conditions we'll have to consider. Okay. So now, diode is forward biased. When diode is forward biased, the diffusion capacitance, is the depletion layer, whatever you have, it decreases. Correct? As you increase the forward bias voltage, as you increase the external voltage, okay, the depletion region, it decreases. So as depletion region decreases, so here I can consider this. Okay, as this depletion region decreases, okay, more and more number of charge carriers flows throughout the circuit. So holes will move towards the negative of the battery, electrons will move towards the positive of the battery. Correct? So as a result, ID, whatever diode current, I can call this as a conventional current with respect to holes. Okay. So with respect to majority carriers, that is ID, diode current, it increases gradually as you increase the value of voltage. Okay, that is the reason CD is given by the rate of change of injected charge with respect to voltage. That is, as Q increases, as the number of charges increases, the diffusion capacitance increases. This is with respect to the forward current. As charge increases, it means the diode current is increasing. Correct?
Yes, ma'am.
So diffusion capacitance, it increases gradually.
Okay, ma'am.
So basically, this capacitance, it occurs with respect to forward bias. Okay. Usually,
Yes,
you'll find these two capacitance under transistors. Okay. There, I'll show you where the diffusion capacitance has come into picture. When I explain amplifiers, we need these two concepts. As of now, the capacitive effects, you just make a note of it. Okay, where it is used and what is the application behind this, all these things we will explain when we take up the unit 2, that is amplifiers. Is it fine?
Ma'am,
Please make a note of these two
Yes, ma'am.
capacitive effects. Yeah, tell me.
Ma'am, what is the relation between diffusion capacitance and voltage, applied voltage?
What happens when you increase the applied voltage?
Potential drop increases.
These two decrease. I mean, this and this are inversely related. This V, as you increase the value of V, forward, as you increase the value of forward voltage, for low value of forward voltage, that is, as soon as this is external voltage, and here if you consider a silicon diode, this is 0.7, correct? So what happens as you increase the value of external voltage? So, who asked this question?
Current is.
Yeah, someone asked this question. Who is that?
Ma'am, Samir.
Yeah, Samir. Yeah, please answer. What happens when you increase the external voltage?
The flow of
Under
charge.
forward bias case. Flow
Flow
of charge carriers increases, correct? So that is the reason I have written ID increases. So as soon as ID increases, CD also increases.
Okay, ma'am. Thank you.
Ma'am, but
Whereas under transition capacitance, what happens? As the voltage increases, okay, what happens? What happens with respect to D? The distance between the two parallel plate capacitance increases as you increase the value of voltage, correct? What happens to this transition capacitance? It decreases because these two are inversely related.
Ma'am,
Did you
but isn't
understand?
diffusion capacitance and voltage also inversely related?
Correct. Here also it is inversely related with respect to this equation, dq by dv.
Ma'am, but right now you said that if we increase voltage, then ID also increases.
Increase voltage in the sense, since we are dealing with forward bias case, as soon as at 0.7 only you'll get gradual increase in the characteristics, correct? And after 0.7 there will be no change in the okay, can you tell me what happens at 0.8 volts?
It becomes constant.
Is it? Samira?
Yes, ma'am.
What happens at 0.8 volts, 0.9 volts?
Current becomes constant. Approximately, it becomes constant.
What happens at 0.3 volts, 0.2 volts, 0.1 volts? Initially, you will get a low value of current. And once it crosses the new voltage, it gradually increases and later it becomes constant. Fine. So with respect to CD equals dq by dv, for lower values of voltage, the charge carrier increases. As the charge carrier increases, the ID value increases. As ID increases, CD increases because these two are directly related. But since it is given by dq by dv, for lower values of voltage, CD increases. Did you understand? With respect to this equation, V and the CD are inversely related, whereas current and CD are directly related. Whereas when you consider transition capacitance, as V increases, the D value increases. As D increases, the transition capacitance decreases. Did you understand?
Yes, ma'am.
Okay. Please make a note of this. At least equations you make a note. So the diffusion capacitance effect is similar to that of a discharge of a capacitor. Next topic of discussion, that is reverse recovery time. Okay, guys, listen here. The next topic of discussion, that is reverse recovery time. So when a forward bias diode is, okay, here the first figure, whatever you are seeing, okay, here you have got two figures. The first figure represents the input voltage. The second figure represents, with respect to the input voltage, how do you get the diode characteristics? This is one of the characteristics of diode. Okay. Okay, when the diode is forward biased, you know, majority charge carriers flows through the circuit and current remains to the maximum. So when a forward biased diode is suddenly reverse biased, when you suddenly switch the state from forward bias to reverse bias, what happens? So from here till here, you have forward bias. When you suddenly switch the state from forward bias to reverse bias, how does diode reacts for this condition? Can anyone tell me? Mihira? Sinchana? Guys, am I audible?
Yes, ma'am.
Yes, ma'am.
Yeah, okay. Please respond. Please respond. You have got a diode. Okay. What happens when you forward bias the diode? What happens when you forward bias the diode? Maximum current flows through the circuit. So that is the reason. For forward bias case, I have written current is maximum over here. Okay. Okay, fine. Here comes the two cases. What happens under ideal condition? How do you get the response? And for practical condition, how do you get the response? We shall explain the reverse recovery time with respect to two conditions, what under ideal case as well as practical case. Okay, so one by one we will take. Under ideal case, here we have a diode. So what is the prerequisites under ideal case? Vaibhav Shetty?
Yes, ma'am.
Can you tell me what happens under ideal condition?
Ma'am, when the
When
voltage
diode is forward biased?
we get high
When diode is
current,
forward biased?
high forward current.
Okay. Current is maximum for lower values of voltage. or voltage, I will take this as 0 for ideal case. Practically, for practical, we will take lower values of voltage, whereas for ideal case, it is 0. Next, this is for forward bias. Next, for reverse bias, can you tell me the condition? Current will be 0. What happens to voltage for lower values of voltage? Current will be 0 for reverse bias case. Correct? So here I shall explain the two, we will explain this figure with respect to two conditions. When diode is forward biased, you will get the characteristics like this under forward bias. What happens when the diode is reverse biased? So here this is forward bias. Okay.
Current decreases.
And current decreases. Current decreases in the sense, shall I make this as 0 under reverse bias case?
Yes, ma'am.
Correct. So the red line, whatever I have mentioned, this marking is for ideal case. When diode is forward biased, you'll get maximum value of current. When you suddenly switch from forward bias state to reverse bias state, diode current goes to 0. That is the reason I have written like this. Okay, this is the condition for ideal case. Did you understand till here?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. 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 Shall we proceed? We shall take up the second case, that is practical condition.
I mean, the graphs,
as
the
you know-
second one is ideal and the first one is practical.
I'll explain. The red one, whatever I have written, that is ideal. The second one, better, I'll change the color. The blue one, whatever I have written, that is practical.
Okay, ma'am.
Okay. So in the forward bias
Yes, ma'am.
state, there are a large number of electrons, correct? From N side diffusing to P side and large number of holes diffusing into N side, P side. So this diffusion process, it establishes a large number of minority carriers each of the material. Now, if the polarity of the applied voltage is suddenly changed to make the diode reverse biased, then ideally the diode should also change its condition from on state to off state instantly, right? So that is what is happening over here. So for a practical diode, this does not happen, okay? Because of large number of minority charge carriers in each of the side, it establishes a forward bias condition. So the diode current, what happens is the diode current simply reverses when you switch the state from forward bias to reverse bias. The diode current and remains at this value, okay, for a certain period of time called as storage time, represented by Ts. During storage time, the minority carriers return to their majority carrier state in the opposite material. Okay, does the diode still remain in on condition in the storage time? After storage time, the current reduces and eventually it will reaches its saturation value after certain time called as transition time. I'll represent this as TT. From here till here it is storage time, and from here till here it is transition time. Okay, so the sum of storage time and the transition time is called as reverse recovery time, represented by T with suffix RR, that is storage time, that is sum of transition time and storage time. So the maximum frequency at which the PN junction diode could be used as a switch, this is basically a switch, okay? Maximum frequency here for small values of current, frequency will be maximum. So for maximum values of frequency at which a PN junction diode could be used as a switch, it can be limited by its reverse recovery time. Once again, I shall explain the practical case. Guys, is this part clear? I shall explain once again. So for a practical diode, what happens is, because of large number, we are dealing with reverse bias. Forward bias, you have understood forward bias case, right? With respect to majority charge carriers, you have understood. Okay, with respect to minority charge carriers, I'll explain. That is with respect to reverse bias. Okay, when the diode, yes.
Ma'am, I didn't understand whether there are two graphs.
First graph, it represents the input voltage. Okay, under second graph, you have two components, two cases. One is ideal case, the other one is practical case. Okay, under ideal case, as you increase the forward bias voltage, current increases. So that is the reason it is following graph 1. And then when you suddenly switch the state from forward bias to reverse bias, you will have to show that it is going to ground level. Means
Current
0. That
becomes
is the
zero.
reason
Yeah.
current becomes 0. That is the reason I have marked it using a red color towards this
Yes,
side.
ma'am. Yes, ma'am.
Okay, that is for ideal case. The red graph, whatever I have written, that is ideal part. Okay, next
Yes,
coming
ma'am.
to practical. Okay, next coming to practical case. Under practical case, the forward bias, it follows same as with respect to the ideal. Okay, only thing is with respect to reverse bias case, you have seen in the characteristics, the practical case. Now here you'll get minute value of current, right? The IS will be say somewhere around nanoamperes or microamperes.
Yes, ma'am.
You'll get minute value, small value of current. How you are getting that small value of current? Because it is due to minority charge carriers. And
Yes,
once it crosses breakdown, later it goes to breakdown state. So you are getting a minute, that is small values of current, and that is due to minority charge carriers. Always make sure that this reverse saturation current is due to minority charge carriers. Okay. So for a practical diode, what happens is due to large number of minority charge carriers under reverse bias case in each of the site, it establishes. Okay, so that is the reason this condition has come into picture. The diode current, it simply reverses, okay, from forward bias state to when it comes to reverse bias state, it simply reverses, okay, and it will remain at this value. It will start from here, it will reverses, and it will come over here, and it will store over here, and it will stay over here for certain amount of time, called certain period of time, called as storage time. I have represented as T with suffix S here in the graph. Are you able to see?
Yes, ma'am.
Yes, ma'am.
Yes, yes. So during storage time, what happens is the minority charge carriers return to their majority carrier state in the opposite material, from P to N or from N to P. Okay, so thus the diode still remain in the on condition during storage time. So that is the reason here IS value, you are getting it as nanoampere and microampere. You are getting minute values, you are getting small value of reverse saturation current. Did you understand? Because for certain amount of time it remains to be on. It won't go to 0. What happens under ideal case, directly when you switch from forward bias to reverse bias state, automatically you can switch the state, when you switch the state from forward bias to reverse bias, suddenly it will go to 0, correct? That is the reason under ideal case, how did we get the graph? For forward bias, we got like this, whereas for reverse bias, we got like this. For forward bias, we got like this, correct? But this does not happen under practical case. We will get small values of current, and once it crosses breakdown, it will go to breakdown state. So this is due to minority charge carriers, and those minority charge carriers, it will stay over here for certain amount of time, and that is called as storage time. Understood? So after storage time, this diode still remain in on, it will remain in on condition in the store with respect to the storage state or storage time. And after the storage time, the current reduces and eventually it will reaches to its saturation value after a certain amount of time, called as transition time or transition interval. Okay, so the sum of storage time and the transition interval is called as reverse recovery time. Did you understand? So this is what happens under reverse bias case. Did you understand?
Yes, ma'am.
Okay, this happens for small value. Okay, this is with respect to small value of time, right? So here we are considering time value as minimum. If time is minimum, what happens to the frequency?
Increases.
Increases. So that is the reason I gave you the statement like maximum frequency at which the PN junction diode could be used as a switch is limited by its dash, that is reverse recovery time. If they mention for minimum period or small value of time, minimum time, then also reverse recovery time. If it is maximum frequency, then also reverse recovery time will come into picture. So reverse recovery time, this is basically a small values of time. Okay, this happens for a small short interval. Did you understand? So this is how practically the graph is varying, right? Here you are getting a horizontal line, whereas here you are getting a small curve, and then it is dropping down to with respect to this breakdown voltage, it is undergoing going to Zener state, that is breakdown. Okay, so you are getting this curve. It is due to reverse recovery time. Did you understand? Any questions? If you have, please ask. Vaibhav?
Ma'am, how long is this
Yes.
recovery time for? Is it in microseconds? Or?
I mean, you're asking this one, right? Specifications of reverse recovery time? No,
No,
not micro. It is nano.
Oh, nano.
Approximately. Okay. It is nano. It is small value of interval. Small
Okay.
values of time. It is nano. Okay, not micro.
Mm-hmm. Thank you.
Okay. Yes. Anybody? Shashank? Pranav Mishra?
Yes, ma'am, understood.
You want me to explain again?
No, ma'am, it's fine. I have understood.
Pramod? Pramod?
Yes, ma'am.
Did you understand?
Yes, ma'am. Yes, ma'am.
Anybody needs explanation? Rohit? Nidhi?
No, ma'am.
Understood, ma'am.
Understood. Okay, fine.
Ma'am, I still didn't understand the practical one.
Okay, you want me to explain the practical case? Did you understand
Yes,
the ideal case?
Yes,
Can you
ma'am.
explain the ideal case?
I'm an ideal case
Omission?
under.
Yeah.
Yes, ma'am.
Yeah, tell me.
In ideal case in forward bias,
Here you have two graphs. Explain
Yeah.
with respect to these two graphs.
Yes, ma'am.
So, first thing is you have positive voltage and you have negative voltage. This is with respect to first graph, correct?
Yes,
So when
ma'am.
voltage is positive, what happens to current? Even current is positive and that is
Current
maximum.
is maximum. Yeah.
That is what I have shown. Current is maximum. Here voltage is
Then
positive.
when voltage becomes zero,
Then
current.
suddenly when we switch from forward bias state to reverse bias, what happens ideally? Current goes
The
to
current
zero.
becomes zero. Yeah.
Becomes zero, correct? So that is the reason I have shown this as zero under ideal case. Here I have shown zero, correct?
Yes, ma'am.
Are you able to see this one?
Yes, ma'am. Yes, ma'am.
Okay. Next. Coming to practical case, what happens is suddenly when you switch the diode from forward bias to reverse bias, the diode won't go to zero state. It won't go to ground state. Okay, what happens is due to minority charge carriers, the minority charge carriers will come over here and it will store for a certain amount of time called as storage time. Okay,
Where
this
do
storage
these minority
time,
charge carriers go?
minority charge carriers is due to reverse bias diode, right?
Yeah.
Majority charge
Reverse
carriers is with
saturation
respect to
current, yeah.
forward bias diode. Minority charge
Yeah.
carriers are responsible for reverse saturation current.
Yeah.
Okay. So
Yes,
those
ma'am.
minority charge carriers will store for certain amount of time and it won't go to zero suddenly under practical case.
Okay, ma'am.
Okay. It will store for certain amount of time. Later, eventually, gradually, it will go to, it will reach the reverse saturation value. It will go to ground level. Okay. So this is called transition. It is getting there is a transition happening with respect to storage to ground state, and that is called transition time.
Okay, ma'am. Yes, ma'am.
And that is the reason with respect to characteristics, you are getting a graph. You are not getting an horizontal line. Okay, you are getting a small curve like this, and later it is increasing.
Yes, ma'am.
And this is due to minority charge carriers.
Okay.
Okay, and the current value is in nanoampere. Current value can be either nanoampere or microampere.
Microampere. Yes, ma'am.
Okay.
Thank
So
you,
this is with respect to reverse bias diode. Next you take down. What happens when the diode is suddenly switched from forward bias case to reverse bias case? Okay, here I shall give you a case study. The effect of fall time on the reverse recovery time. The minimum fall time can be ensured to be, that is, okay, let me change the pen. Okay, fall time and all as of now it is not required. I'll do one thing. As one of your friend mentioned, I shall give you the important specifications with respect to PN junction diode. Please make a note. This is very, very, very important with respect to diode characteristics. There is one case study with respect to this diode. This I'll give you under case study in the case study class. First, let me finish the theory part. The important specifications of a PN junction diode under this, and also I'll give you typical values, Okay, take down the first specification. Take down the first specification, reverse saturation current. Reverse saturation current for silicon, the reverse saturation current measured in nanoamperes. For germanium, the reverse saturation current is measured in microamperes. So these are called typical values. Coming to second specification, that is forward voltage drop. For silicon, it is 0.7 volts. For germanium, it is 0.3 volts. Are you making a note?
Yes, ma'am.
Yes, ma'am.
Next.
Yes, ma'am. Yes, ma'am.
Okay, next. The third specification, reverse recovery time. Reverse recovery time. The specifications can be either 100 nanoseconds, 50 nanoseconds, so and so forth. Coming to fourth specification, that is power dissipation. It can be 1 watt, 2 watts, etc. Coming to fifth specification, reverse breakdown voltage. Reverse breakdown voltage, 40 volts, 50 volts, 100 volts. These are the practical specifications of a PN junction diode. Please make a note. Is it over?
Yes, ma'am.
Yes, ma'am.
Okay. Okay, fine. We shall take a few numericals with respect to diode. First question, please make a note of this circuit. This is 10 ohm resistor and these two are silicon diodes. This is negative, this is positive, 10 volts. They are asking you to find the current which is flowing through the circuit. Okay. Can anyone tell me what is the value of current which is flowing through the circuit?
One amp.
Is it 1 ampere? Check the direction once again. Is it 1 ampere or minus 1 ampere?
-1.
-1 amp.
-1. Okay. Guys, can anyone explain? How did you get? Let others also understand. Can anyone explain?
Ma'am, because the two silicon diodes are a forward and reverse bias, therefore they cancel effect of each other.
Correct.
So only
Correct.
that external things will remain.
Correct, exactly. So here the negative of the 10 volts, it is connected to positive. I show you. Here you have negative voltage, it is connected to positive of the diode, and positive of the diode is connected to negative of the silicon diode. And these two silicon diodes are in opposite direction and it cannot conduct. Okay. And since these two are reverse biased, right, and I can show this as an open switch. When you write an equivalent circuit, this is open switch, and here you have a 10 ohm resistor, and here you have a battery of 10 volts, negative, positive, and here you have 10 ohm. Now we have to find the current which is flowing through the circuit. So this will be, here you have, this is minus, right? This is minus 10 volts divided by 10 ohms. If you take, you'll get minus 1 ampere. Understood?
Yes, ma'am.
Okay.
And this
Next
-1
question.
is only with respect to direction, right? We can't actually have
Direction.
right?
No, current, well, current, that is, you are getting a negative in the sense current, that is basically a current direction. It is flowing in the reverse way. That is the reason.
Okay, ma'am.
Ma'am,
Okay.
if both the diodes are forward biased, will any current flow through the resistor?
If both the diodes are,
Forward biased, would any current
okay,
flow through the resistor?
yeah, it will flow obviously.
But how much? How do we calculate how much?
When you consider, okay, we will consider the forward biased diode and we will solve. We'll take a few more numericals of that kind.
Yeah, okay.
Okay.
Sure.
Yeah. Next, I'll take those type of circuits. Okay.
Yes.
Next question. Make a note of this. Are you able to get? This is 8 volts input plus 8 volts. 1.2 kilo ohms is connected in series with that. Here you have 4.7 kilo ohm resistor in series with the silicon diode. They are asking you to find the output voltage across this, and also they are asking you to find ID. ID and V0 you will have to calculate. Now you have to apply KVL. Can you apply KVL? So how are you going to apply KVL? Here, listen, here you have 8 volts, right? I can write it as 8 minus, current is flowing like this. Okay, so this is, current is flowing in this direction, positive, negative, positive. So I can write this as minus 1.2K multiplied by ID. Okay, minus 4.7K multiplied by ID minus 0.7 volts equals 0. Did you understand?
Yes, ma'am.
Shreyansh,
Yes, ma'am.
did you understand?
Yes, ma'am.
Shashank, simple KVL I have applied,
Yes, ma'am.
and I have to call upper ends I have considered. Polarity is very, very, very important here. Vaibhav,
Yes, ma'am.
did you understand the KVL, whatever I
Yes.
have written, KVL
Yes.
equation?
Yes, ma'am.
Who did not understand, please let me know. I shall explain again, because these are the
Ma'am, can you
basic
explain
problems.
once?
Okay, I shall explain again. Here you have 8 volts. If you write this circuit in terms of an equivalent circuit, how do you represent 8 volts? Positive, negative. 8 volts. Here you have a resistor. Here you have one more resistor. Here you have a diode. And here you have a ground potential, means negative. Across this, you are going to find the output voltage. This is silicon diode. This is 4.7 kilo ohm resistance. And this is 1.2 kilo ohm resistance. This is 8 volts battery. You are going to find the current which is flowing through this circuit, and along with the output voltage. Output voltage and current you are going to calculate. Okay. Now, in order to find ID, we shall start from here. What is the drop across here? Are you able to see? This is plus and this is minus. What is the drop over here? Are you able to see? Ohm, Telang.
Yes, ma'am.
Can you tell me what is the drop over here?
8.
No, here this is plus 8. Okay. Can you tell me the drop over here? Okay. Let me write the equation, and then I am taking all upper ends, that is rising potential, plus 8 minus 1.2K. Current always flows from positive to negative, so therefore I have to minus 1.2K. Resistance value, it is always multiplied by the current in order to get the potential. Okay, and here this is minus 4.7K multiplied by ID. Okay, minus 0.7. This is plus and this is minus. Correct? Minus 0.7 volts, and that is equal to 0. Did you understand?
Yes, ma'am. Yes, ma'am.
Now you calculate ID, that is 8 minus 0.7 divided by 1.2k plus 4.7k. How much you'll get?
Ma'am, 1.23
1.24 milliampere.
milliampere.
1.237 milliamperes.
1.24
Fine.
milliampere.
Okay, fine. Okay, no problem. Find the output voltage. How are you going to calculate output voltage across this? Okay. Current is flowing like this, means this is positive and this is negative. Right? So therefore, this positive of this V0, it is connected to positive of 4.7. So therefore, I will take plus 4.7 multiplied by the current value, that is 1.237 milli. Okay. And the diode plus 0.7, and that is equal to, okay, you need not equate it to 0. You can find the output voltage. If not, the other way around, I shall also show you the other way. In order to find the output voltage, you will have to always consider a ground potential. With respect, this is ground potential. With respect to ground potential, you apply the KVL from bottom to top. When you apply the potential from bottom to top, can you tell me what is the drop over here? What is the drop over here? Are you able to see the arrow mark?
Minus 0.7, right?
It is plus 0.7 here. I have written an arrow mark, right?
Okay, yeah,
This is plus
yes.
0.7. Here, one more arrow mark I have written. Can you tell me the drop over here? It is plus 4.7k multiplied by current, correct? And that will be equal to V0 value. Did you understand?
Yes, ma'am.
How much you'll get?
From 6.5139.
6.51 volts.
1.513.
I shall show you, okay, what is KVL? If you consider only this particular branch, you are getting so and so output voltage. You may also get a question like, why aren't we applying this particular branch? What happens if you apply this branch? Can anyone get me the output? Here also you can apply the sum of these two branches. Okay, if you consider this branch also, you'll get the same output voltage. If you consider this branch also, you'll get the same output voltage. If you want, you can verify. So with respect to the other branch, whatever I have shown you, this is plus 8 volts, and here you have minus 1.2k multiplied by ID. So solve this and tell me how much V0 you are getting. 8 minus 1.2k multiplied by ID you do, and tell me how much V0 you are getting.
$6.51
You are getting same value, right? Even this is 6.51 volts. Either this or this. It is your choice. However you want, you can apply. Did you understand? First, we'll take a few more
Yes, ma'am.
numericals of this type so that you'll not have any confusion. Which class you have next?
Maths class.
Maths, is it? One more question we will consider, and later we will wind it. Next question. Input is 12 volts, a silicon diode connected in series with a resistance. This is germanium diode and this is silicon diode, and this resistance is 4.5 kilo ohms. They're asking you to find VO1 and VO2, and also they're asking you to find the current, total current ID. Question here is to find ID, VO1, VO2. These three parameters you are going to calculate for the given circuit. Yes. Can anyone tell me? What is the drop with respect to silicon diode? It is 0.7 volts. What is the drop with respect to germanium diode? It is 0.3 volts. Correct? Now, in order to find ID, it is 12 minus 0.7. Always remember, in order to find I, the numerator values are voltages and the denominator values are resistances. Okay. So numerator only voltages I'll consider, that is 12. And here you have minus 0.7. And what is the drop over here with respect to germanium diode?
0.3, ma'am.
Minus 0.3. I'll consider all upper ends. So minus 0.3, correct? Divided by the resistance values. Can you tell me?
Minus 4.5 K into ID.
No, resistance value minus 4.5. I am writing in the denominator. So what you'll get? It is 4.5 kilo. When you write in the equation only, you'll get minus 4.5 K multiplied by ID.
Yes, ma'am.
When I write in this form, that is numerator divided by denominator, then this will become 4.5 kilo ohms. Can anyone tell me the answer?
2.4.
2.44.
2.44 milliamp.
2.4 milliamperes.
Milliampere.
Okay, this is the value of forward current. Now, can anyone tell me what is the value of VO1?
0.7 volt.
0.54.
VO1 is here. Correct?
0.54.
0.7.
Wait. VO1 is here. So in order to calculate
0.7,
VO1,
right?
it is 12 volts minus 0.7. If you do, you'll get VO1. How much?
11.3.
11.3 volts. Correct. This is the answer. In order to find VO2, how do you calculate? This is across germanium diode. Did you understand? If you want to find VO2, it is across germanium diode. What is the drop across germanium diode?
0.3.
0.3 volts. Done. That is the answer. If not, or if you apply KVL, you can apply KVL from here to here. Can you tell me? It is 12 volts minus 0.7. Okay. Minus ID into 4.5K. If you do, then also you will get VO2. Either this or this. Whichever method you want, you can apply. Either this branch you can apply KVL or that branch. How
Ma'am,
much you'll get?
VO1 is there, no, ma'am. In that, why we should do like a 12 volt minus 0.7?
Come again. How do you find the output voltage? In order to find the output voltage, you have to consider from the battery potential only, right? There has to be some reference voltage. You can't find VO1 with respect to only one element alone. You can't consider diode alone in order to find the output voltage. Some of the potentials with respect to the entire circuit you need to consider. That is what KVL says, right? The potential differences across each of the elements, you'll have to equate it to 0. Did you understand? You can't consider
Yes, ma'am.
silicon diode
Understood.
alone. Okay? Yes. So this is also one more way in order to find VO2. Either of the methods you can follow. Anybody has got any doubts? Any questions? Please ask and get it cleared now itself. Sachin,
No, ma'am.
Omisha,
No, ma'am.
the numericals, did you understand?
Yes, ma'am. I understood.
Yes, ma'am.
Vijaya Raghavan, did you understand? The numericals, did you understand? Okay. So please go through once again whatever I have done. Okay, further if any doubts you can ask me tomorrow. Okay.
Okay, ma'am.
Thank you, ma'am.
Yes.
Yes, ma'am.
Okay.
Thank you, ma'am.
Okay. Thank you guys. Thank you. We'll wind up. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.